Hello and welcome to the class. Today we'll be talking about pointers. Majorly you will see two types of questions in exam with respect to this topic. And one will be pointed to a variable, the other will be pointed to a function. Today we'll be talking about pointer to a variable. Basically every variable or object that you store onto memory through a program will have a value and it will also retain an address. It has to be addressable. So now we will use pointers, which are itself variables, to refer to those addresses for doing some manipulation tasks. So what is a pointer? A pointer is itself a variable that stores memory address of another variable or another object. The object can be structure, it can be class object, it can be any primitive data type, variables, let's say integer, character, floating point, and all those others. Or it could be pointed to arrays also. So pretty much pointer stores the address of the variable or object. Why do we need to store addresses? Sometimes we need to refer to the addresses in order to do some kind of manipulation. There are some basic manipulation tasks that we can do. We need to let's say add two numbers, and we need to add them through their memory addresses. We use pointers to do these kinds of operations. And it's the backbone of the low-level memory manipulation in C. The thing that I wanted to talk about is, let's say we have a pointer P and we have a variable X. As I said, it will have a value. It will have an address also. Pointer itself, being a variable, will also have an address of its own, but the value inside the pointer would be the address of this variable that we want to store, let's say 2000. In some time we'll be seeing how do we actually refer to variables like this. Now the basic manipulation tasks. Before going to basic manipulation tasks, I want to take a minute here to see how the pointer initialization is done. Pretty much how do we refer to addresses of different variables. So basically what happens is we first mention the name of the data type of the pointer. It's necessarily mentioned, so let me call it data type, and then I'll have a pointer name, and then I will use an assignment operator and use this symbol is called as ampersand for dereferencing operator, and then I will have a variable to which it refers. This is the syntax. In actual practice, an example would be something like this. Imagine I have a pointer P and I want to store the address of a variable named X and with the data type that has integer. Now I want to make one point here. This integer will take up some space, right? And this pointer will also take up some space. The question is how much space? Basically, it's dependent on the machine type, it's dependent on the compiler type, it's dependent on the operating system. There are a lot of factors. The basic low-level thing behind this is that, imagine this is the structure of the memory. Now the memory is organized in such a way that it is addressable. So basically, each block of memory will have an address. Let me call it 2000, let me call it 2001, 2002, and so on. So basically this memory will be addressable, okay? And each block of this will hold some data. The length of the data will also depend on the type of the machine, okay? And the number of addresses that are addressable will also be dependent on the type of machine. The basic formulation behind this is that the number of addresses will be equal to the length of address bus of the CPU, and the length of the data that fetches at any point in time will be dependent on the type of CPU as to how many operations, length of operations that it does at particular instant of time or in one CPU cycle. Okay, so this is pertaining to data bus, this is pertaining to address bus. In older compilers, pointer always used to take 2 bytes at least. Okay, and there could be, so if a pointer, if the size of pointer was 2 bytes, which is 16 bits, the total number of addressable locations would be 2 power 16. Okay? And this was same for all the compilers. They would always take at least 2 bytes. Okay? And now I want to store the address of this x, which is sitting somewhere here. So imagine x is a value, let's say 10. It's stored at 2001 location. So what I do is I'll make a pointer named p and store this 2000 location there. So now p points to the address where 10 is stored or where x is stored. This is how pointers are initialized. There is one more concept that sometimes we need to do pointer arithmetic, which I will discuss next in next lecture. For now, let's do a quick question. Here it is. It was asked in GATE Computer Science 2025. We have a variable x whose value is 16640. And recall the story that I told you that it has an address. Okay. And each variable will take some size depending on the type of the data. In older compilers, it was given in the question that it will take 2 bytes for integer and 2 bytes for pointer. Now we'll see actually how this is stored in memory. The value is 16640. We know that every decimal value in a very low level setting is stored in the form of binary. Okay, so what we'll do is we'll convert this 16640 into a binary version of this. So basically I'll say what is the binary code of this. I have pre-calculated it, and to determine this we'll use a simple formula. And so on. Okay. It was given the idea it takes 2 bytes. So basically, I have converted this 16640 into a 2-byte representation in the form of binary. Now this has to be stored in the form of in memory somehow, right? But it was also given the question that the memory is byte addressable. So at any location, 8 bits will be stored at maximum. Now the question is, this is a 16-bit long number. How do we store it into 8 blocks of 8? So basically some chunk will go here and the other half will go here. But which half? There is a concept called as little endian and big endian. In little endian, the least significant bit part, so I am marking the least significant bit and most significant bit. The half from least significant bit up to until the calculation it makes 8 bits will be stored in a lower address. Okay, so basically from this 0 until 8 zeros will be stored here, and then remaining bits would be stored to a subsequent address. This is how little endian operates. Big endian would be simply the opposite of this. The most significant bit chunk would be stored at a lower address, and the least significant bit chunk would be stored at a higher address. The question was given that it was a little endian problem, so hence the least significant bit part will be stored in the lower address. This is it. Okay. So now we know that this is how it is represented in memory, right? Now I have a pointer to this memory. The address of the memory is 2000. I have a pointer to that. I have another variable p, which points to this location, 2000. Whenever pointer has to store multiple addresses or a chunk of addresses, it will always store the base address. The base address is 2000. Even though the integer spanned 2 addresses, 2 blocks of addresses, it will always store the block address, which is the base address. And now we know that pointer points to this location. Okay. The third line of this this piece of code is that now we'll simply print the value of p, basically star p. What happens when we have star p? It means that whatever p is pointing to, you go to that address and print it. Normally, if this would have been %d, we would simply be printing this whole integer. This would be printing the value of 16640, right? But since this is typecasted, what happens is this pointer, even though it points to a place that stores integer number, it will now treat it as a 1 byte number. 1 byte number, because character takes 1 byte. So now pointer points to a location. By using this typecasting, it will say that I only will have to fetch 1 byte. What is the value of this 1 byte? 0000000. 8 bits, all zeros, which is what? In decimal 0, right? And similarly, this, if this had been written as p plus 1, it would simply go to p plus 1, 2000 plus 1, which is 2001. It would be printing the this sequence of 8 bits, which is what? Which is 1, 2, 4, 8, 16, 32, 64 plus 1 is 65. So this will be printed as 65. Now the last part of this is that it is %c. %c means it will further convert this integer to a character type. 65 is converted to a character type, which is its ASCII code of A is 65, so hence A will be printed. This is how pointer arithmetic plus typecasting plus pointer to a variable type question would be expected in an exam. With this, I'll stop here. Thank you for watching. See you in the next class.